All right, so good morning, everyone. My name is Brandon Dotson. I'm from the University of Central Florida. I'll be showing some initial results from our geotechnical measurements we've been doing in vacuum. But before I get into it, I'd like to just take a minute and acknowledge the passing last week of Dr. Ed Stone. Among other things, Dr. Stone was my graduate advisor at Caltech so many years ago, but an absolute founding father in the field of planetary science and space exploration. Served as the project scientist on Voyager for 50 years, starting in 1972. Of course, the first spacecraft to visit Neptune and Uranus and enter interstellar space. He was the director of NASA's Jet Propulsion Lab for 1991 to 2001. So during the return to Mars with the Sojourner, I guess it's a rover, the operations of Galileo out at Jupiter, and the launch of Cassini. So no pressure for me as a dumb graduate student to sit down with him every Friday and try to show him how my code in C++ wasn't working. But just wanted to take a minute to highlight that. Okay, so if you are not a civil engineer like I am not, just to kind of give a quick overview of what we're talking about in terms of geotechnical properties. Some of the key features are things like shear strength, cohesion, and internal angle of friction, and they're related by this thing called the Moore-Coulomb criteria, which is essentially the slope of a line. And so when you plot that, basically you end up with different normal loads give you a different amount of shear strength. And it doesn't quite hold true when you go to low normal loads or reduced gravity, but for this experiment, we're just assuming it's linear. So why should we care about geotechnical measurements? So I'll give you a few historic, albeit on Mars, for some of these examples of where this bit is in the rear end. So first, the Spirit rover gets stuck on Mars, right, and eventually ended its mission because of low cohesive soils that it drove into. The heat probe on InSight, which failed to really burrow because the material was loosely packed and cohesionless. And then here's a moon example, since this is ELS. So when Apollo 12 landed, they landed about 200 meters away from the Surveyor 3 spacecraft. And in doing so, sandblasted that spacecraft. The astronauts brought back pieces of Surveyor, and we looked at them under a microscope, and you can see all the pitting and cracking and damage from that plume exhaust. So, and that is really because of shearing forces from the exhaust. So, and why do I care about that? My research mostly focuses on plume surface interaction and that exhaust factor, but really cohesion and shear strength are a major component of that. So being from UCF, we have access to a lot of high fidelity simulants, including Highlands and Mare simulants, as well as some older ones like BP1 and JSC1 that we used in these experiments. And these really have the same mineralogy as some of the samples we've seen during Apollo, as well as the particle size distributions for some of those samples as well. So what we're doing here essentially, and this is probably hard to see in this picture, but we have this custom made little box where we fill it with regolith and we essentially shear it and measure the force. So with that, we put different normal loads on, much like that linear feature I showed you earlier with the equation. And that allows us to actually fit that and figure out what cohesion is for that sample. So we do this for one particular density, and then we repeat this over and over and over again and vary the bulk density and see what we get. And we do that by vibrating the whole sample. So I'm going to build this because this plot can be a little confusing, so I'll just kind of build it. But the last one I showed you with the line, that's essentially one point on this plot here. And so what I'm showing is Lunar Highland simulant. This is in atmosphere, so exposed to water. And so we repeat that at a number of different densities, and that's what I'm showing here. So on the x-axis is density and cohesion on the y-axis. And what we see is that there's actually an exponential increase in cohesion when you increase the bulk density. Now, I'll continue to build it here with the rest of the lunar simulants that we did, again, in atmosphere. And we see a similar trend where this region over here is for the dusty or fine grain simulants, just lower density, but still exponential in growth. So with that, we can check it against some of the previous missions to the moon. So namely, looking at the Luna data, we see it's generally in that range. As I click forward here, Surveyor made some measurements, again, kind of in that ballpark. And then this larger window for Apollo, which we see the numbers that we're getting are actually pretty realistic compared to the real measurements. So I'll overlay now some Martian simulant just to kind of show that that's a similar trend regardless of what the mineralogy is. It's more particle size, as well as some of the insight data range as well. So, and then we did this with glass beads and then looked at previously published results, and we're getting similar results here. So all this to say that there is a huge change in the cohesion of a sample, and it's largely based on density. So that was one of our main first findings. Next, internal angle. So this is a super busy plot. This shows all the different simulants we've looked at: lunar, Martian, controls, glass beads. And you can see there's kind of a trend here. Again, I compare this to previous data from the actual missions. We see it's kind of in the ballpark, as well as some of the Martian ones. And generally, it kind of falls along this range here, where we see that there is generally an increase in internal angle when you compact it. And that kind of makes sense, right? You would expect that. So that's, again, in atmosphere. So now vacuum test, and we took that same setup and put it inside this vacuum chamber because we're just running two like smaller roughing pumps. We're only really getting down to pressures of like 160 to 170 millitorr. But with that, we basically repeat that whole trial to see, okay, what happens. So this is the same data I showed previously. Now I'm just showing LHS1 in atmosphere, and then 1D, the dusty fine grain material in atmosphere. So once you do this experiment in vacuum, what we find is that LHS1 plots somewhere down here, and LHS1D, the dusty simulant, plots somewhere down here. So that is definitely weird, not what we expected to see, a decrease in cohesion when you put the sample in vacuum. So that was kind of an interesting finding that we were not expecting. Similarly, if we look at internal angle of friction, this is that same, all the data I was showing before. I'll just pull out here in blue and green LHS and LHS1D. And similarly, when we do these measurements in vacuum, what we find is that there's actually an increase in internal angle of friction. And that's both for 1D and for regular LHS. Again, not really what we expected to find here, but an interesting result. So with that, I've been talking about shear strength and cohesion and internal angle, and another way to think about this with regard to bulk density is it's essentially a 3D space. If you put all of those points together, you get kind of this curve that sort of looks like this, where on one axis you have bulk density, the other is the normal force, and then your z-axis is shear strength. And so when you look at like the Lunar source book or other sources, you'll see a huge range in what these values would be. And it's largely because you're moving around somewhere on this 3D surface. And so with that, when we put it into vacuum, if you kind of squint, this edge that I've highlighted here with the red line is essentially that same exponential curve that I was showing for in atmosphere. So when you put this in vacuum, that line actually decreases. And as I mentioned before, there's an increase in internal angle, which is essentially this axis increasing. So what you're finding is when you put the samples into vacuum, this whole 3D surface sort of shifts, which means the entire behavior of the material from a geotechnical perspective is different under vacuum conditions. So that's also weird. We did not expect that to sort of go that way. And what's going on here? We have a few thoughts. This is still very much early work. We're kind of working through it, but essentially there's a number of things that contribute to cohesion and shear strength of a sample, right? It could be the particle shapes and sizes, interlocking of grains, the moisture content, but essentially by putting it in vacuum, whatever that combination or balance there is changes. And so one thing that might not have dominated in atmosphere, like electrostatics or moisture content, is going to behave differently. And so all of that to say, if you're using these samples and you're using them to test instrumentation or to test building stuff or building structures in preparation for going to the moon, the behavior does change when you use it just in open air vice in vacuum. So with that, I think I'm way ahead, but happy to take any of your questions. Thank you. Yeah, thank you. Easy questions only, please.
No such luck. Stan Starr from Imperial College London. What we've found is that if you don't bake out the soil prior to testing, that when you evacuate it, you fluff it up, basically. You decrease the density, all sorts of, and previous tests I was involved in Kennedy Space Center, we'd actually see plumes of gas flow up through as you evacuated it. So I mean, we found that there's a NASA standard that Julie Kleinhen's put together that talks about how you prepare lunar regolith samples for various kinds of testing. We found out that conforming to that is really worth doing to get solid results. Just a comment.
Yeah, no, that is a great point. So I guess I should mention the whole reason for sort of looking at this and doing a sensitivity study. So there's a test going on at NASA Langley this summer where they are using a lot of regolith and wanted to determine, hey, is it worth the energy of baking all of this sample? So in this case, we didn't bake it for these numbers here. We're going through now and baking materials to see for different periods of time and different temperatures to see what's good enough with regard to that standard. I will say for LHS 1 and 1D, the exolith simulants, they actually behave pretty well under vacuum. They didn't really like geyser or anything like that. But when you use BP1, for example, it's pretty nasty under vacuum if folks are planning to use that material. I think it's largely because there's so many fine grain particles in that just cling on to water, and so when you pump it down, it does do some crazy things. But yeah, there is a standard, and they do set temperature and time constraints, and we're mostly trying to see if there's a way to lessen those for those tests this summer. So, thank you.
Thank you.